We're going to keep that in mind. Ellie?
Isn't it because like the satellites, we have like the gravitational pull like on like kind of like, okay, so like here's the Earth, and then there's like the gravitational pull like outside Earth, and there's like space.
And so
we have like gravitational pull.
The satellites go beyond the gravitational pull and they get into space and there's no more gravity,
Well,
and
like,
so they're weightless?
No, they have like enough mass to.
Because what you're saying is what 90% of people believe, right? We learn as children that there's no gravity in space. We see pictures of astronauts, jumping around or bouncing around the space station with their hair all crazy because there's no gravity on their hair. And we think, oh, well, there's no gravity in space. That's why the astronauts are weightless. If you go home and ask your parents, most of them will probably say that, because when do we ever learn differently? That's not actually the reason, but so many people believe it. I'm really glad that even though that's not exactly where you were going, I'm kind of taking us there, because that is such a common misconception, right? Space, there's no gravity in space. So the astronauts are on the space station or any of that, so they don't, that's why they're weightless, right? That's why because there's no gravity in space. Not quite. Jeffrey was really, really close. Jack, do you want to add?
This is a bit of a stretch, but when you first see a rocket launching, when they're sending a satellite into orbit, it shoots straight up, but eventually it will make what's called an orbital shift, where they tilt the rocket in a certain direction, so that as the rocket climbs, if you were to put it on a chart, it would have an arc around the Earth. And
it's inserting into orbit, exactly.
And they keep accelerating, gaining altitude and speeding up at the same time, to the point where the arc reaches around the Earth.
So we're increasing our velocity, not just going straight up, but going forward. Both of those are tying into the correct answer. So, when I throw this ball, and tell you what, Lee, throw the ball, but pretty gently, not very hard. Alright, so he threw the ball. What eventually happened to the ball?
It stopped.
It came down. It stopped. He had aimed it a little bit more to the side. It would have hit the ground. He was trying to make sure that it didn't, so Miss Kick didn't have to bend over. Thank you, Lee. So it hit the desk, but it would have hit the ground. Lee, throw it a little bit harder. All right, what do you notice about it that time? Did it still hit the ground? Mm-hmm. What was different? He put more force on it, so he...
It went up a little bit.
It went up a little bit? Okay, it went up a little bit instead of going straight down. Dalton? It went further, exactly. By putting more force on it, it went further. He's putting horizontal force on it to make it go forward. What's the vertical force that's pulling it down to the ground? Gravity. At the entire arc that this is going to follow, gravity is pulling on it the same amount, but it's only until the force going forward dies out enough, kind of, it decreases to the point that finally all we have is gravity pulling on it, and it hits the ground. Alright, so we have horizontal force, and we have vertical force. And they're going to work together so that it makes an arc. Alright, horizontal and vertical forces. Now, I want you to imagine, alright, so this is what projectile motion is, right? Projectile motion is watching this entire arc. Where else have we heard of the term projectile motion? Anybody? Anybody go deer hunting? Nobody? Deer hunting? I'm sorry, did I?
I sometimes went squirrel hunting.
Squirrel hunting. What projectiles do you use when you're squirrel hunting?
You have to okay, I was taught really bad. Like, my brother taught me how to shoot with a BB gun, so it wasn't like the same, but we were taught like which direction like the wind changes, get back to like
Okay. Right, there's a lot of different variables when we go into it, but if we're just talking about plain old vanilla projectile motion, what is our projectile? Matthew? Bullets, exactly. What's the force coming from? When you were shooting off your BBs, Ellie, where did the force come from?
It came from like on the trigger and the thing kind of shooting it out.
Okay.
Spring.
No, actually not a spring.
Well, with bullets with gunpowder and
Right.
gunpowder.
Right. exactly. We have a controlled explosion of the gunpowder, and it's going to push our projectile force. So that's providing the horizontal motion. What's providing the vertical motion? Always gravity. So if you are a horrible shot, and you're out in a field that goes for miles and miles, and it's very, very flat, and you take aim at the deer, and you shoot, and you completely miss, what's that bullet eventually going to do? It's eventually going to drop and hit the ground. It's going to take a while because it's got a lot of horizontal force, but eventually it's going to drop and hit the ground. So that's projectile motion. So Sir Isaac Newton imagined, well, what if I went up to the very tallest mountain and I threw the ball harder than any person could possibly throw the ball? What would happen? Well, the ball would travel for maybe a couple miles, and then it would fall and hit the ground. What if I threw it even harder than that? What if I threw it so hard that once the ball finally started dropping, as it's dropping to hit the ground, as Jeffrey said, the ground is falling away from it because the earth is a sphere. It's curved. So as I'm throwing this ball and it's starting to fall, instead of it falling just like that, it's falling, but the earth is falling away from it at the same time. Then we would have a satellite in orbit. I have a picture, Sophie. Alright, so here's our super duper cannon. And the first shot that it makes, it shoots the ball so far and then it splashes into the ocean. The second ball it shoots, by the time the ball starts falling, the earth is falling away from it as well. So now, it's always falling, but it's falling in a circle. Does that make a little bit more sense? A little bit? Okay, satellites in orbit are continuously falling towards the earth. But since the earth is curved, they continuously fall. Well, how come they never hit? An object in motion tends to stay in motion until another object or another force acts on it. There's not another force in there, right? There's not another force. So it's going to continue circling the planet. Now, there is actually some forces. If we have some air molecules, not a whole lot, but some, what is eventually going to make this stop? What force is that going to be if we have some air molecules that are way, way up there? Jack?
Fluid friction?
Fluid friction, exactly. Air resistance. Now, there's not a whole lot, and it's pretty easy to give this another boost so it'll go back up into orbit again. But if we want to throw a ball so that it goes in orbit around the Earth, it's going to take about 7,900 meters per second of velocity. So that much force to throw that ball. Think you can do it? No. Alright, so this is what it looks like on that ball, on that satellite, as it's traveling around the Earth. So you can see the surface of the Earth is curved. We are just constantly falling towards it. But as we're falling towards it, that edge is dropping off. So this is actually, I believe, on the space station. There's a thunderstorm, all the lightning strikes. And you can see, someone was asking in the last period, oh, is this a time-lapse photo? I think this is actually real time. Whoa. That's how fast it's going. Because the satellites, like the space station and the communication satellites, well, some communication satellites, weather imaging satellites, those are all in low Earth orbit. So they're going to see a sunrise and a sunset every 2 hours. A day for them, it takes them 2 hours to go around the Earth. So, they're going to see a sunrise and a sunset 2 hours apart from each other. Alright, so this is less than 1,000 kilometers above the Earth. This is low Earth orbit. Mapping observation satellites. The higher we go, what did you guys notice about the longer the string was? Ella Clemens, what did you notice about the longer the string was when you were swinging the yo-yo around?
It took it longer to get around, so it was slower.
Exactly. It slowed down. It took it longer to travel around. It's going a longer distance, and so it takes longer for it to go around. So the higher the orbit is, the longer it takes for the satellite to complete its orbit around the Earth. And we can take advantage of that, right? If we have a GPS satellite, it kind of needs to always stay in the same place, right, to let you know where you are. If you're moving around and the GPS satellite is moving around, then you're never going to know where you are, right? Those GPS satellites need to stay in the exact same place. So they're in what's called a geosynchronous orbit. Geo means Earth, synchronous means it's staying the same. So they are always staying in the same position above the Earth. But they're orbiting. How can that be? Lee?
They're orbiting with the Earth.
Exactly. They are taking the same amount of time to orbit around the Earth as it takes the Earth to make one rotation. So it takes them 1 day to orbit around the Earth. So it's like they just stay in the exact same spot. All right. So tonight for homework, please complete the Think It Over question that is on page 362. Describe the object's motion. How do you know that the string exerts a force? You do not have to, everyone does not have to have the observations, but you need to reference the observations that you make. Make a claim and back it up with evidence that you actually observed, okay? That's the homework. I have a short video. Apollo 9 was the Apollo mission that they tested the lunar lander, the lunar module. And they had to figure out, well, if we're going to get to the moon, and, you know, how can we actually hook up the command module that has the astronauts inside of it to the lunar module that two of the astronauts are going to use to go down onto the lunar surface. So this was from the mission. They actually took video of it. Because think about it, guys. If you sped up the yo-yo, and granted, it didn't actually change its distance, but when you made it shorter, it sped up, right? That's actually orbital mechanics. The faster you go in orbit, you're going to change the orbit that you're in. So if they want to catch up to the lunar module to catch it, so they can dock with it, so they can actually go to the moon and explore the moon, they had to be really careful with how they did that. Otherwise, they'd end up in different orbits, and you'd never be able to catch it. So this was just something pretty cool that I liked, that I thought I would share with you guys. So that's the lunar module, and that's Earth down below. So this took place in, I think, like 1968, maybe early 1969. Apollo 9, which one was the Apollo that landed on the moon? The first one too? No, Apollo 13 never landed on the moon. No, 11, very good. So this one was before Apollo 11. They had to kind of figure out everything. They worked together in the space program. One mission figured out this is how we control the command module. Another mission, Apollo 8, the one right before this one, actually circled the moon so they could see what it would be like to actually travel to the moon. How could we get into orbit around the moon, right? There was a particular thing they had to figure out, how to insert themselves into orbit around the moon so they could do that. So this was... So the calculators that you guys carry around, the iPads that you carry around, have more calculating power than what we just saw, than all the computers that took us to the moon. And that's including the ones that were back here on Earth as well, that were helping. Yeah. And all right, any questions? All right, we have maybe 1 or 2 minutes. If you guys would like to get started on homework, I can come around if you have any questions. It is the Think It Over that goes with the Discover activity on page 362. I'll write it up over here.